C, and you try to determine the velocities and the concentration rates plus mechanical potential by optimizing this functional. Okay. So, okay, and then okay, you can from there you can make an incremental approximation. Okay, so I could define. I'm try to write here. Okay, so if I keep the notations of the other one. Can define it's like this, but I'm going to remove consider the C, so that's why I put I3 just like that one was V3, okay? So, but my this has been time integrated, so it's clear. Okay, so we have a epsilon of C. It is a constant. It should be a constant for our purpose. So it makes this in 0. I got this one. Okay. And this one. Again, I will write this to save a little bit of space on the wall. Okay, so I put the minus here. I prefer to keep it here because this is how we defined it before, so there should be a, of course I should change this to minus that. Again, it's a quadratic function, so it's the same thing for our case. Okay, and then we have the loading, together with the volume and the force, and the increment of displacement. We realize that okay, we need time to change it, but sign error here, so it's plus. Here, and okay, so last time we started to look at the special case. We could, and so one thing with the TFC is that okay, here we are going to minimize on the C. Okay, so we can look at two cases. Okay, so the general case we did it last time. Okay, I showed you that this is when you minimize with respect to C. Going to find a relation between the derivative of C, mu, and there is a term coming from here, okay, which is purely algorithmic. And this term will vanish if alpha is equal to 0, for example, or if there is no explicit dependency. And this is the case for the linear situation. Okay? And then we introduced also so in that case, okay, in the case where I don't have this or sort of, let's say I put alpha equals 0, for example, there's no dependence here. the C is only in this part, okay? Then I can analytically eliminate it by introducing the Legendre transform of this, okay? So remember last time I introduced a function C star from mu, which would be psi of epsilon C, or technically make some room there. Okay, okay. And so this means I take the C, which is such that it is related to mu and epsilon by the constitutive relation. Okay. And this gives me a function which is only on of epsilon and mu. I eliminate C. Okay. So in that case, if I put this into there, I can define in the end, define maybe a function only of two things. So this amounts to doing this is the I which is there actually. Okay, in the specific case, so I explicitly do the minimization, but doing the minimization is actually amounts basically to work with FC star. Okay, and we had that this is equal to E minus 2n times 0. And the rest is the same, okay? So we will do a blank here for the moment. Okay. And the rest is the same, okay? And there was a delta here, of course. Oh no, sorry, it's this one. This. Okay, so if I don't have a dependence here, but this is really a function, I don't have any C anywhere. Okay, so in that case, I can really do that. Okay. Okay, so now, otherwise I should. Put a C here of what, I don't know, maybe something of epsilon represent something like this. Okay, but usually we don't do this because this is I told you already last time, computing this analytically. Okay, like this it's feasible, it's just this, but okay, no, if you have to find the analytical expression for a complicated, for something else than a quadratic function for C, this becomes complicated, and then you have to put in something in here. Okay, so this pure two-field formulation. Okay, maybe we can keep it for the case where this doesn't exist. Okay.
So,
yes.
why did you wrote in red, please?
So epsilon n plus alpha and mu n plus alpha. Okay, typically we want to avoid this. Okay, so. Okay, why do I do this? Just I want to show you the connection with the previous case. So if it's not there, okay, so again that ones. Okay, let's show you that. This is equivalent to this. Okay. If I don't have the red part, because in this model I don't have the red part, this is this actually. Okay. I can do it. Okay, so for example, okay, it's this. Okay, it will be the one be this one because I will put dynamics in the mechanics is statics. Okay, but this will be the same thing. Okay. So just but okay, so before going further, okay, so if you have a nonlinear model and things like this, the best implementation is to use this. But okay, if you have a simple linear case, we can use this one, okay? But this is a special case of this, and this is more general, better in general practice. Okay? But okay, let's look. Okay, so we started from a case where we could write this free energy like this. We have okay, and this we did last time also. This as a result. Probably this is what we have on your notes from last time. Correct? No mistakes from me. It's what you must have somewhere. This is somewhere from last time. It's okay? Just make sure that I can make it. this equals something this way.
It's good.
It should be this, okay? Right. So, okay, so, okay, so, no, okay, this time, okay, I'm not considering it, okay? So I've got only u and u. So I have to write the stationarity of this with respect to u and u. Okay. So again, I will write the I'm going to make it a bit compact to make it. Okay, I'm taking variations on u. Okay, where is u coming? It's from here. So I'm going to have this. I've got the deep C star d epsilon times variation of epsilon, but this is the grad delta u. Okay? And then I've got the force terms. Well, I think I did this last time, so I can go fast on this one. Here. Okay, this should be 0 for delta u. And then if I recognize that this the function which gives me the stress is a function of epsilon and u. Okay, if I divide, I've got okay, so this is this, okay. Yeah, there's a minus here. Okay.
That's the whole first part, but
And okay, actually this is what defines this force. This is what defines the C minus C0. Okay, so this is the relation we have different from the beginning, but okay, now it's expressed in terms of mu and epsilon. You could also redistribute it if you want, so we could also write this as H minus okay, so this is an elastic tensor at constant chemical potential, while this one is an elastic tensor at constant concentrations. Okay, so this okay. Comparing this to this, so I've got my H minus n minus n times n minus h epsilon. So the epsilon delta u is this, okay? This is what I call oh, okay, so it's a symmetric part if I take the symmetric gradient if you want. But since this is symmetric, it doesn't change anything. This is the okay, this is what I wrote. Epsilon delta u here is the virtual strain.
Professor,
Yes.
I'm actually sorry, it's very hard to see the writing on the book. I'm sorry.
Because of the reflections or
No, it's very difficult.
it's very
It's very difficult. What you just write, I cannot see.
It's an epsilon of delta u, okay? It's just this one. Just showing you that this is the same as this. Okay?
I'm sorry.
Yeah, sure. Yeah, no, it's discuss and
It's a little better on this
just
side.
so that-
You have to go to the projector. But then you have this one.
Can you move the table there? Yeah, sure. Oh, you can see.
Now I'm gonna start talking to you.
Okay, so the point is that you just get that, okay? So it's, I think I did it last time already, so it's just the same thing. Now, if I try to, or if I do the other derivation, the other stationary conditions, I need to this one. Okay, so where is the new? Okay, so I want to remove this as I go, but I got new here. I got this one also. This one. Okay, so I need to this space, so I need to do this. It's not going to work. I've got that ET. So this is relative with this argument. And here. And this. And I'm left on these two things also here. This one. Okay, so this is going to be the same thing as here. To observe this, we need to Okay, so then I carry the sign over here in the beginning. Okay, we're going to see because here, again, this was written in terms of rates, okay? So here I get this relation, but in terms of the values at Tn plus 1. Here I've got a small difference here, which we're going to look at. Okay.
Professor,
Yes.
this looks familiar, but what is the difference between this one that you're doing now and the one you did the other day where it's like, it has a J in front of it and then it's epsilon mu, gradient of u.
Talking about this in this sense.
Yeah.
No, okay. I guess this is the same, but then I'm going to replace this into it and show you the. Or maybe I did. You mean I already did all this?
I don't think so. Like,
Okay.
I don't.
Okay, so the J was the local quantity.
The what?
The J I defined as a local,
Local. Okay.
something which was inside the integral.
Okay.
Okay, the J was, well, it's erased now, but this was the result of the minimization rules.
Okay.
J was a density, I remember well, and this is global sink. It's integrated. There was no integral in the J. Okay. No, the thing is that okay, we want to see things, connection between this and this. Okay, so this is a time discrete version of that, the specific one you need to see. Okay, so this is written in red form, but okay, this corresponds actually to the fully implicit version of that. Okay. That is a case where I would have replaced this by. Okay, now I need to explicit to develop things. So, for example, this. D over d nu, okay, this is our d nu. Okay, we find that it's equal to minus mu plus epsilon over h, okay? The Cn minus C0, okay, I could also rewrite it in terms of the mu1 and the epsilon n, because what was when I was doing I move from here to here, okay, so I have a minimization over C of, it's not there with the transformation. Between these two, I've got the relation which I put here actually. Okay. So you can write this in a way or another, but the chemical potential is defined as Hc minus C0 minus an epsilon, or you can define it in this way. Okay, so this is basically to go from here to here. I just replace C minus C0 by this, and I get this. Okay, so that's how we did it last time. Okay.
Why is mu The gradient of delta u, mu, a vector.
Yeah.
Because I didn't say.
That's
Okay, vector is not the gradient. Okay, so this also, this block is going to become convenient to write it as mu n plus m epsilon n over h. Okay, so as a consequence, for example, I will go back here. I replace this by this, and this is actually this. Okay, so this stationary condition. Okay. Okay, so we realize these are the same things, all right? Okay, so I can, if you want, I can write them like this. If I take this part and this part, put them together, okay? And I'm going to take this part and this part and I'm putting them together as well. Okay, so I treated this block. Okay. Now this one, again, this is a quadratic, take phi c as being a quadratic function. Okay, I'm not wrapping the space here. Never enough words in these rooms. Okay. Remind you that we are in this case. So phi c is given by this, okay? Or by this. Okay. So derivative of phi c with respect to g is just kappa times gc. Okay. So I get here plus delta t, and okay, I'm going to do that. Delta kappa times gc. Okay. I see the gc is minus. Itself times the grad of the okay. And then the rest, which is the same as this, if you compare it to this one. Okay, so
Why is the value negative?
okay, so this is the thing which I'm checking now. And the minus sign also when I derive it. be a minus in the end, so that's why I'm made a mistake somewhere. So like here. Okay. So the idea was to take the so this is supposed to be let me write it directly there. So this okay. Oh, why this is- I stick to this notation because it's one. So this is supposed to be minus 1/2 this. Okay, so now if I write here's the function of minus value. So when I take the derivative, normally write this with the minus which comes from here. Becomes a plus. So that's what I try to do here. But then, okay, so yes, no, but I should do. So there is a minus here. This is correct. So this is my other things which is not. Signs errors everywhere. Yeah, so this will be a minus in the end because I started from a minus quadratic function. So it should be like this. It's okay? Yeah. Okay, so I want to compare this with this, and probably I have to pass on this one. Close. Oh no, yeah, no. It's fine, it's correct. It's just there's a minus sign between this one and that one. So if I look this, I can divide everything by delta t, for example. Okay. Can put a delta t here, delta t here, delta t vanishes here, vanishes here, vanishes here. Okay. This is correct, right? And so when I do that, I get this one, I can do that. It's a discrete approximation of new dots. Okay. This one. Okay. It's a discrete approximation of epsilon dots. So here I've got this one here. This one gives me this time here. This one gives me this one. Okay, and I think I didn't put the boundary word in that case, but I get this. Okay. But okay, with a minus sign in front of the whole thing. Okay, so this shows just this is just to show that okay, the evaluation principle is indeed equal to this in this specific case, but of course it's true in the more general case too. Okay, so okay, we go to erase. So that's it. I can start here. Right? Maybe to the system. Okay, so the last thing I want to show you now is that okay, you can also derive the finite element formulation directly from there. Okay, so what you can do is okay, okay, so let me just first let me rewrite for a moment that okay. So this is the I2 actually. If I formally eliminate the C, and then we can see how if we don't eliminate the C. I'm not going to rewrite again the false parts, but it's just put in the right. All the false is the extended part. Okay? You can focus on that. Okay, so the I can do is I can try to do a demo approach of this. Okay. I'm not going to redevelop everything because it will take just too much space, but okay. Here, okay, just fundamentally so we can write something like this. So this U is so some nodes of nodal values. Function of time times shape function. Okay. And okay, I also need to put the use the same thing. Here I make a choice. I use the same shape functions for displacement and chemical potential. It's not absolutely necessary. I could use different meshes. Okay, it's one thing I didn't talk about interfaces between meshes, and I have a few slides which I treat later. Okay, in this case, we use the same mesh for displacement, for the chemical potential, same shape functions, so same approximation, same shape functions. Okay. Okay, so in that case, okay. What can I, okay, so I can put this into this, okay? And to do the discretization, I can compute this incremental energy for the discrete case, okay? Okay, so for this I need to develop this a little bit because it will be easier. I develop the thing, okay, as I did before. So I just developed this, okay, I simplified it a little bit. So the H mu, okay. This is what this is what I wrote during the course. This H mu is the H minus exclude and just develop the square here. I use symmetries over there. I don't even need to use symmetries actually here. But okay. So this is a more, this looks more like this, if you want, like this one. I've got a quadratic term, a bilinear term, and another quadratic term. So here I'm not going to redo the whole derivation, but okay. If we look term by term, okay, that's what I want to do. So I take the first term here, okay? So, well, let me do this. So I want to compute this. If I inject my finite element approximation into this, okay, I have an integral of this, okay, these are gradients of displacement, so I'm going to have gradient of shape functions, okay, so we've done it already in the thermoelastic case, so I'm not going to redo the whole thing. But this, the contribution of the first term is going to be something which that can be write it like this. Okay, I've got the other terms which I explained it. After finite element discretization, we can replace this by a quadratic function of the arrays of nodal displacements. Okay? And again, this is the classical elasticity matrix, the integral over the domain of h nu times the gradients of the shape functions. Is the one we've seen before. Okay? And I call it E because the k I'm going to keep it for the kappa later. So the terms coming from this one. Okay? Okay, these are, we've done this for the thermoelastic case, just okay, instead of T it's mu now, but it's really the same thing. Okay. Okay, and also this can be 2D, 3D. Okay, the expression of the matrices are a bit different. But you can, okay. So this term, this bilinear term, is going to be bilinear term in nodal values of u and nodal values of mu. Okay. So this we use the B matrix for that. Okay. So if I keep the convention we used for the B matrix, remember it's not a symmetric matrix, but technically, normally I should be able to write it in this way. Okay. But okay, if you want, I mean, the point here is that it's a bilinear function of mu and u through epsilon, so I get a term like this. Finite element discretization. The B is very similar to what we, in the 1D case, is what the one we developed for the thermoelastic case. In 2D, it's going to be a bit different. But it's a rectangle, I mean, this one is symmetric. This one is a rectangular matrix. Because, for example, it means that it will have as many lines as the number of nodes times the number of special dimensions, so 2 or 3 number of nodes. And as many columns as the number of nodes. Okay. And okay, here, this term, ellipsis star and give me cognitive function in U, so I can write it. Okay, so there's a 1/h, so I don't know. Okay, this is just it's not really a capacity matrix because it's if I fundamentally I can write it. I can use C. There's a structure of mass and capacity matrices, except it is computed with a coefficient 1/h. If I make my analogy with the tunnel problem, that's what I call. It's very similar to what I could see in the tunnel problem. Okay. So this is for this term. Okay. Okay. So then I can quite immediately say this, okay, also. In the end, okay, it's the same thing, except now that I'm going to write things in terms of there's no influence because I'm going to minimize it's a constant. It doesn't really matter. But actually, yes, I'm going to. So quite. Okay. Okay, so this I got this term. Okay. If we look at this, okay, that one is a bit special. Okay, but maybe not so much actually. If I compute the integral or omega, so mu minus mu n. Okay, I need to compute this one. Okay, so here, this is when it starts to become a bit different, a bit, okay, so, I can treat it in different ways, okay, but, okay, this one is something. Sorry. It's need to be okay. But there's so there I've got a question which arises. Okay, what is the representation of C? Okay. Okay, so do I make? I don't need to make a finite element operation of C. there is no gradient, I don't need to compute this gradient or anything. Okay? So technically, this is okay. I think U and UN I can put the shape functions. It's like a source term. Okay. Okay. So this actually I can write it as a okay, so and let me, I'm not going to use RC because it's going to be, this one was there. Use the R3 with the, okay. So R is something which is defined node by node. And okay, what is the okay, let me put an N here because it's it depends only on values at N. Okay. So, and this, okay, I can, technically, how do I compute this? I'm going to do a sum over the elements, okay? So I put a P which say that it's the shape functions defined over the elements. Okay. And this itself will write it as a okay, do integrations by those points. Practice of okay, so normally I can C0 is a constant for everybody. Okay. So this looks long like this, but okay, in practice it's not. So when you do finite elements, this means you need to store the concentrations at the integration point. So this is the integration point number I of the element E. Okay, so if you have a triangular mesh, how many integration points do you use? Okay, yeah, 3 is better, yeah. Okay, yeah, for this you need 3 because the phi is a linear function. To the in 2D you can use only 1, it's okay. For quadrangle, you need to use 4. For triangle, you use 3. I think you can use 1 for different instruments. Anyway, so this is okay. The point is that we are going to okay. we are storing the concentrations at the integration points. Okay, so we suppose that we have you suppose that we have access to the information about what was the concentration at the previous time step at each integration point.
So is RNA the same as the Rn that is in the equation you wrote to the left?
Okay, so this is an array. Okay, column array. It's dimension of the number of nodes because it's conjugated to mu. These are the I suppose it's a line array of values of mu at nodes. So when I do this product, okay, I can see that this must be also an array of the same dimension as mu. This to be okay. That was okay. Just trying to explain you that the value associated to node A is given by this. So you have to assemble that at some point. Okay, you can also do it in a different way. Okay, so there are two options. Okay, you can do this. An alternative. Maybe it's easier to do a connection with what we did before. Okay. Okay, it always depends. Okay, you do discrete. When do you discretize? Do you do manipulations before discretizing or after? Okay, but that's what we did before. Okay, so you remember, you know that this is. We wrote this. Okay. If we explicitly enforce that, so if I don't want to keep track of C, okay, so which is okay because maybe I don't want to completely eliminate the C. Okay, I can do it. Again, this will work if there is a balance on C here. Okay, so we're just okay. But then in that case, okay, so this is going to go omega. So this means I want to evaluate C from an interpolation of mu and epsilon. Okay, so I don't store things at the integration points. And it amounts to interpolating C if you want, but not directly through the dependence. Okay, but here I'm just putting more information than there because I impose the fact that C is given like this. In that case, I've got a form which is a bit different. So if you develop a little bit, okay, you can split this in two parts. You have the mu minus mu n times the mu minus here. Okay. So this will be if I use the having something like this. Okay, so this is actually what we did for the thermoelastic case. We didn't write entropy really at that point. Okay. So this is when I'm in the continuous case. Writing this way, this is the same as this. Okay. Okay, but the moment I do a spatial discretization, I introduce a different approximation from here and here. So I get slight difference. If the mesh goes to very fine, and you won't see the difference. But okay, you have to make a choice. Okay, so in this case, okay, so this is two options, okay?
What is in the first version of it? We have a weight.
Yeah, it's integration weight. Okay, this is the standard thing in integrand. So you replace the integral by, you evaluate the integrand at the number of integration points. You weighted sum of the values. Okay, you should have seen this in the fundamental course. So, for example, if you have a triangle, 3 integration points, each weight is 1/3 of the surface. Triangle. Okay, if it's a line, take 1/2 the length. And the integration points, okay, they will be located at the triangle. Okay, yeah. That's why I write GP, because I typically use Gauss discretization. What is called Gauss points. So it's a special case of quadrature, of approximation of integrals. Gauss integration scheme. You have many different options.
What point can you repeat it?
Okay, so here, my son. Okay, so typically this is I have a triangle, okay. I need to do an integral over a triangle. I'm not going to do the integral, because that's my function. So I'm going to evaluate this, and this. Okay. So where do I put my cross? And how much weight do I give it? So what are the xi and the wi? This depends. Okay, you have rules to do this. Technically, you can do what you want, but if you have to have a good approximation, there are optimal points, optimal location, and optimal weights to put them. Okay, so I'm not going to go into this, but there is a special. So 1/3, 1/3, 1/3 in the terms of barometric or barycentric coordinates. Okay, you have. So these are the. Yeah, okay, we're going to go into detail. Okay, you have rules and you have tables in the books to decide how to pick your xi and the W1. Okay. And the classical rule is the Gauss Cool. You have Gauss Legendre, you have Gauss Lebon, there are many variants. But this, okay, you have to look in front and look to find this. We'll discuss this a little bit when the Phoenix, okay, you have to decide what you use. Somewhere you say use it's implicit, but you choose one. Okay. But okay, let's maybe just to make the connection more easy with what we've done before. We are going to retrieve exactly what we did for thermoelasticity, except that instead it's chemical deflection instead of temperature. Okay? But what we did in the thermoelastic case, the equivalent to this chemical diffusion mechanics case, is this choice. Okay. And again, this choice works because I don't need the concentration, because I didn't put the dependence on concentration here. I got a very simple model. Okay. The moment I get a more complicated model, I cannot write this anymore. It's not a linear relation, and I cannot eliminate C so easily. Okay. This works only for the linear case. Okay. Okay, we can insist on this. Okay, I'm almost done. Okay, so I got the approximation for this, and now I need it for this. Okay, so but this one is easy. Okay, so it will be the integral of the domain of delta t. And phi c is a quadratic function in my case. So this is going to be times kappa. And grand, okay? There's a 1/2. Okay. So this is my okay. So if I put my space discretization into this, I'm going to have gradients of shape functions in this. So very much like this one, okay, except that it's not the same dimension. The gradients, these are gradients of a scalar field. These are gradients of a vector field. It's not exactly the same matrix, but this is going to give me this. I can write it as okay. I got delta t is left there. I got the half is there. I can write. Here I can write it like this. K is symmetric, positive definite, like almost positive matrix. Okay. So if I put everything together, okay, with my finite element approximation, I created. I've got an approximation of my incremental energy. Let's try to put this all together, okay? So we can see. Okay. Okay. Just this is let's call this I. Okay. It's a constant. It's going to play no role in my minimization, my optimization. Okay. So otherwise it's going to be very long. Okay. It's just okay. And then I've got this term. So this one, let me, okay, I got this one, yeah, this which I'm going to write under this form, okay? So, say we have this thing like this, okay? Okay, and then the last one, so then there's a minus, so I should have this one, is delta t, okay, of mu exposed k mu, okay. And then these forcing terms, we're going to have something normally it's a minus okay, this is the mechanical loading. No, this is we've done it. So this is the integral of the volume forces times the displacement. Okay, actually technically it's should write it like this. Because it's on delta U. Okay. And I got the resolution. Okay, I'm not going to details into this, but okay, you get this thing which I didn't write. These are linear functions of u and u. Okay, so this will be linear functions of the displacement array and the catch array. Okay, so I say that I want to minimize okay, so this is my initial information. So what I'm going to do, can leave a link, but okay. Okay. Okay, now it's just algebraic optimization. Okay, so what the quadratic function I want to minimize. Can take the derivatives of each with respect to each thing. So I take the derivative of this with respect to u. Okay. This one gives me this. Then okay, second term will give me this. Third term nothing, fourth term be constant no. And this one gives me nothing in terms of okay, this nothing and then I got the okay. Okay, so this is what we had. This looks very much like what we had in thermal elasticity. Okay, and then this was temperature and chemical potential. And then put the inertial terms. So this is a static equilibrium. If there was no coupling, this would be just an elastic problem. Okay, but okay, there is coupling, so there is a mechanical loading coming from the mechanical potential linked to the swelling. Okay, sorry, there's one thing that I need to show up here. It's a matter of definition. If you go back to the terms in brackets, there was also with delta t in front of the slide. I want to put it there explicitly. Okay. Just a matter of defining R. Okay. There will be a delta t in the integrals which construct R, so I should just leave it explicitly there because okay, so this is the, if you want, this is okay, this is the minimization with respect to u, gives that, and the maximization with respect to mu. I need to write the stationarity condition. Okay, if I write them in the same order, I've got okay. This does not depend on mu. This depends on mu. With this, I need to transpose it. Okay. I got the C mu. The I doesn't provide anything. The last term, okay, you need to pay attention here. Okay, so there's the mu here, this is constant, but it's going to be there. I got a plus C mu n and a plus G transposed mu n. Okay. Then I get the diffusion term. Okay. And the loading term in the end. So it's, I can reorganize this a little bit if you want. Okay, so we'll do this. Okay, the mechanical case is not complicated. static equilibrium with some forces. Okay, and the second one, I can reorganize it if you want. Okay, so I've got the u minus un here, which is hidden. Okay. But same thing here with the C. This. Okay, so okay, I could put the n terms on the right hand side and solve it. Okay, this gives me the system I need to solve to get u and u for the right time step. Okay. No, just okay. Compared to what we've done before, okay. Want this, I can always do this thing, for example, okay, This corresponds to, in terms of time integration scheme, this corresponds to a fully implicit or backward order. Yeah, because okay, and then put this is supposed to be n plus 1, okay, the value at the end of the time step, the value at the end of the time step, the f, if you go back, this was also approximated at the end of the time step. Okay, the u is the end, so this is the basic finite difference approximation of u dot, approximation of mu dot, and it's also the final amount. So there is no beta method here. It's in the sense of okay, beta method is beta equal 1 if you want. Okay. So this means that my Bayesian formulation allows me to retrieve what I'm used to if you want. This single case, okay. Except that I don't have the flexibility to change the time integration. Okay. This would make it much more complicated if I wanted to flexibility. To do a midpoint approach, a generalized midpoint approach in variational form is not so easy. Okay. What comes out of the variational form is the implicit expression. Which is okay because we know beta equal 1 is a stability conditions in everything. Okay, so it's larger than 1/2. Okay, this was an explicit form. It works. We know it works. Just a few final comments, but I'm going to put So the slides in a second. I'll let you finish to write this and then erase it after. But okay, so this works again because I'm assuming I'm in the simple linear case. I get all this. Okay? If I'm not in the linear case, I can keep some of it, but not all of it. And okay, that's what I want to discuss. But from using the slide we had before. Okay. Okay, so if I'm not linear, I'm not going to be able to write this as a quadratic form. Okay, not necessarily as a quadratic. This is not going to be a quadratic form. Well, okay, there will be no, this will be not valid anymore and so on. So it needs to be a bit more complicated. I will not go into the whole thing, but you can still look a little bit on the. Okay, so okay. So in the general case, I'm not going to try to eliminate the C. Okay, I will work from there. So if I put, yeah, maybe I'll try to write it out. So if I try to put a finite element approximation in here, okay, so what I'm going to do, I'm going to do this. I'm going to write that epsilon, okay. Okay, from epsilon I'm going to go maybe I can construct. Okay, so I have integrals here. Okay, I'm not going to write the whole thing, but hopefully you can follow me. So this integral I'm going to replace it by a sum over elements. Integral over elements, and each integral over elements is going to be a sum over Gauss points, integration points. Okay. So when I compute this integral, forget it for the moment. When I compute this integral, I'm going to sum. I'm going to make a weighted sum over the value of C, evaluated at all the integration points. Okay. So I need to evaluate the epsilon at each integration point. Okay? And this formally, I can always write it as some big matrix, I call it G for, let me call it G epsilon. In here, I've got the derivative of all shape functions at every integration point, every element. Okay? Just to give you the idea of the. Okay, so but this is how I construct my my approximation of this incremental energy. Okay, so I can do this. So here, I could also write it as G epsilon of U1 if you want. C, I need C, so I assume that I know C again at each integration point. But this is going to come from the minimization, so for the moment I don't know C. Again, as I explained just before, I suppose I know Cn at every integration point from the previous time step. Okay. The mu, okay, the mu I can write it if you want. Maybe I can write something like this. Okay, this notation we typically use. Okay, so yeah, this is. Okay, so you could. these are the nodal values, okay? And these are the Gauss point values, okay? So you can interpolate, that's what it means. You have shape functions, you can evaluate the value of mu at each process of my triangle, okay, as I drew before, from the nodal values, interpolate some specific points, okay? If you know the integration point, you can evaluate the integration the shape functions. You can construct something like this. So just to show you, okay, I'm not going to practical implementation of this, but you can, what I want to show is that you can replace everywhere epsilon, mu, and the same thing, the grad mu here. This one, okay, okay, so you can also write it as a collection of the gradients of mu at each integration point. You can write it as a big matrix with the derivative of the shape functions times the column array of the mu's, okay, another value, okay, and so on. You can write things. So this means, okay, oops. So, and okay, now I've got the inf of C, but the C is a local thing. So at every integration point, I can evaluate C by doing the local minimization. This, for a given array U and a given array mu, so for given values, nodal values of U and mu, I can evaluate this at every integration point. This is the integration point, this I suppose I know the integration point, and so on. This I know, and this I evaluate. Okay, the C and in here I know it. Okay, so at every integration point I can do a minimization over C, find the C for given U and E. Okay, so this I have to do in the code. I need to do a loop over all integration points, compute this. I cannot build my big matrices directly, okay? And then, with this result, I got the function of U and mu, and then I can try to solve for U and mu by doing a Newton minimization, which typically minimization you can do by descent method, like can be linked to Newton-Raphson or have other optimization methods. I'm not again going into that, but okay, the only thing I want to say is that in the general case, solve this, you need to carry the concentration to the integration point, and it becomes what people call in the mechanics of material, they call it the internal variable. So it's like plasticity. If you were doing plasticity, you have to do the same thing. If you do damage, you have to do the same thing. You have to recompute the plastic strain at every integration point, every time step, every iteration, and so on. So it becomes a bit more complicated, okay? I'm just trying to show you that it's something like Phoenix, okay? Just to try to illustrate what it means. But okay, so this is difficult to illustrate without going deep into coding. You're going to do a little bit of coding Friday, so I think it will be enough. Going to that, I mean, it requires a lot of. But typically, okay, that's what you need to do if you want to solve a complete problem. Okay? So just the last slide to discuss. Summarized here. Okay, so okay, I didn't show it, but the system I wrote, it involved symmetric block matrices. because I divided these are second derivatives of the function, so it will be symmetric. Okay, it's an inf soup, so you could try to do inf and then soup, then inf again and then soup again, or not, or just once. But if you just do one inf and then one soup and then you stop, there's no guarantee that it's going to be good enough. Okay? That's an interpretation for loss of stability. And somehow, what I try to hint at the last comment is that, okay, so in general, you start to need to have keep concentrations at the integration point, so actually you can increase or enhance the model by adding damage, plasticity, and making a very complicated models with all the coding you want. But the structure remains the same in the sense that everything is hidden in this local minimization. The global boundary value problem, the Feynman structure is the same. It's just that the minimization with respect to C is modified. This is local, the integration point level. Okay? So you don't see from the Feynman problem. Okay, time to stop now for this morning. So remember Friday, we try to do some coding. I will, so you will start from the files which are the hippocampus, okay? So either with the Phoenix or pure Python. In all cases, I'm going to hopefully I will prepare this for by Friday. A skeleton of a notebook that you have to fill. And what I want in the end is a notebook with text. I don't want you to write a report in your work. You just give me okay, I'm going to give you a mark for this. I told you it's part of the mark.
Do you do it on the day or could we work on it after?
No, I'm not going to ask you to give it back in the evening. No, we'll let you time after. So guys, we discuss this.
No.
Okay, if you prefer, I can do just one exam and all your bets on one thing. If you want, okay, there's no issue with that. For me, but okay, it's less work for me if you do one exam. I think it's better for you to, okay, so, to have this, thing, okay, you won't have to give it back in the evening, Friday evening. I'll let you a few more weeks.
Yeah, but it's okay now.
Okay, I want you at the end of the 4 hours. Okay, it can be 4 hours and sitting there. I want you to do something. So from the you're going to try to implement this. Put everything in a nice Jupyter notebook with comments.
After 4 hours, you have to check our code.
Sorry?
After 4 hours, you have to check our code.
No, I give you more time to give it back.
Okay, okay. It's not your mark. You just would have to submit the assignment.
We still get the mark after the thing was.
That's a good thing.
Yes.
That's a good thing. That's a good thing.
I'm not saying it's a bad thing, I'm just surprised.
No, we thought that next Friday you're going to mark on the based on what you did in the class.
Also.
This is over. Can we go?
Yeah, okay, but this is okay.
Getting the time to do it.
It's not easy to, okay, I want to trace of what you did in the class. Okay? And so that's why I don't ask you to write a report, I will just want a trace of what you did, and the best and simplest way for everybody, I think, is just you put everything in a Jupyter notebook, so you put your comments, one commented code and to have a nice commented code. The Jupyter notebook is really the best option. Okay? You can write text, you can write data, you can format it to titles, structure. This is Even